Let's go ahead and get started. Thank you everyone for joining. This is the 19th meeting of the Technical Working Group. It's been quite the slog. So to start with today, just to give everybody kind of a recap or what we're going to be going over today. Documentation will be first and foremost, then we'll be talking about a recap of the last meeting to catch everybody up. From there, we will be talking about the single hour versus the day model, which was a question that came up last time. We'll go into the temperature binning to solve our temperature bias issue, how the clustering the daily usage arose out of the temperature binning, where we're currently at with the hyperparameter optimization, and the next steps. So to start off with documentation, we have been working on getting updated documentation for all of OpenEEmeter. This can be found here at this website, the https openeemeter.github.io/eemeter. This is complete for the daily and billing models, and as we are still currently working on the hourly model, we will also have that documentation out by the time that the new hourly model is out. To give you an idea of what that documentation looks like, I'm actually going to go to the website here and give you a look. So this is there's just a general understanding of what a lot of EEmeter is used for and the general concepts. Within the daily and billing model, it breaks down what the general concepts that again here are, including how we use splits to ensure that we are not having too much seasonal bias. And then we start to give some more detailed explanations of how you run EEmeter for the daily billing model, including the imports, what kind of data you should expect to put in, and so forth. Then at the top, if you want to go more in depth, we have our reference API so that you can dig into seeing, basically these are all of the encode doc strings that we are exposing to the website. And so then you can go through and see what is what. Hopefully this helps everybody be able to begin using OpenEEmeter, as we have had some requests for improved documentation. Any questions on that, or concerns, or suggestions? All right. Let me go back to slideshow. So just to recap, we have looked at many different models. The current one that we have pretty much decided upon is using a simple elastic net model, which is about 3 times faster than the existing Caltrack 2.0. And the new model inputs are, in addition to the temperature and observed, is the GHI, which is a form of solar irradiance, as well as other potential supplemental data, though this is more of a research input than anything else. And I should also note that interpolation is a necessity with this new model, whereas this was not necessary for Caltrack 2.0. Now, previously, OpenEEmeter 3.0, or Caltrack 2.0, as I just called it, its output is for each individual hour, whereas the current model's input is 24 hours at a time. Now, each day has to have a complete set of features, or we have to exclude that day, just due to the nature of how the elastic net is set up. We're using sklearn's elastic net, and we have to interpolate any nans in the features, and this means any nans in the temperature, the observed GHI, any supplemental data. It must be a complete set. Now I'm going to pass this off to Armin. Armin, would you like me to click through for you, or would you prefer to share yourself?
I'll share it. I'll share mine.
All right.
This guy here, and just let me know if you are able to see it.
Yep.
Okay, let me go to the slideshow. Okay, So this was actually one of the questions that I think either Ethan or Mustafa asked in the previous session that we had. So we went ahead and explored a little bit between and compared the model between per hour prediction and daily prediction. So what do we mean by day and hour model? Just to clarify, we are talking about hourly model, but different type of prediction. So per hour means look at each hour features and predict 1 hour at a time, and then go to the next hour all the way to the whole data set to cover the whole data set. And the way we do it, hour one features normally we have temperature. You can have solar irradiance, GHI, or um, other features as well. And you're going to have a couple of categorical variable, month of the year, day of the week. And because we are talking about per hour model, we need to kind of mention what hour of the day we're talking about and we want to predict for it. And then based on all of these information that we have here, we predict one output at a time. This is per hour model. And then the version of point of view for the hourly model would be look at the whole day of features inside of day. What are the features? You can say you have 24 hours temperature, 24 hours solar irradiance, what month of the year we are in, and what is the day of the week. These are going to be your time series features in the beginning and categorical features at the end. This is one vector. And for each day, at one time, we predict all of the 24 hours worth of observed data or the AMI data, smart meter data that we have. And we do that for all of the days inside of our data set. By exploring that, we have explored that before, but just to bring it up with the new version of the model that we have. As you can see, we have a table shows PN RMSE, which is normalized RMSE basically for population. And the first row shows the non-solar residential population. The second row shows solar residential. As you can see, the new model, the day version of it, has the best performance compared to the both of the models, both Caltrack and the new model per hour. Which kind of makes sense for me because we are looking at more data and then we are connecting the dots between different timestamps for all of those 24 hours within the feature which we are mapping to the observed data. And so these numbers that we can see here, the model computational efficiency, it's for the previous version of the analysis we did. We've done a couple of other stuff, which I'll explain in the next couple of slides. But basically, per hour model is 6 times faster than Caltrack. Day model, which predicted per day, is 7 times faster. But in general, we have a better error metric. And that's why from now on, we're sticking to the per day prediction model. And it's faster and it's better. But these numbers changed a little bit.
What do you mean by it's learning better and the features better with the day model as opposed to the hour model?
Okay. So basically, if we are looking at each hour and mapping the features to one number, one, you're going to have more noise because inside of 1 hour, you tend to have more noise rather than looking at the whole day. Two, it's basically, let me close this. Two is basically when you're predicting 24 hours worth of data, other features for that set of data set, and they need to contribute to predict all of the timestamps for that day, 0 to 23 or 1 to 24. Okay, so basically number, for example, if there's any irrelevant feature in the timestamp number 12 that can help for the 13, we have the option in the model to do that. But the per hour doesn't have that. It's kind of isolated per hour.
Okay, thanks.
Okay, if there's no any other question, we move on to the problem that we have here. Okay, so as you remember, we had a little bit of problem with bias. So we were doing great in RMSE, PNRMSE, which is normalized RMSE, in almost any point of view, population, parameter ID, different section of the data. But bias was a little bit off compared to the Caltrack. What do we mean by bias? Bias is basically the difference between the observed and model. I mean, model minus observed, basically. And some parts we had positive bias, some parts we had negative bias, and the actual size of the bias was a little bit bigger than Caltrack. So in order to solve this problem, we had two options. One, binning the temperature as what we basically had, not exactly the same, but similar binning mechanism with Caltrack 2.0. And basically for each day, we come up with squeeze that data, 1 day of data to one metric, and kind of cluster, cluster, bin the temperature based on that metric for each day. So for example, let's say we have the mean value for each day, 360 days, 365 days, 365 data points, bin the temperature, that would be your temperature bins. Or we could have linear temperature with the second option. We could have different element-wise linear models, or we could use different kernels to linearize the model. Travis, is there anything that I didn't cover here, or any question? Because after this, I will go to the temperature bins and all of the extra modules that we have in the new data, in the new model.
Yeah, I will say that as far as linearizing the temperature response, it's probably something that would be an improvement even over binning by temperature, but it's also something that would require a significant amount of R&D work that we just have decided that it's better to get a new, better model out now as opposed to trying to get the perfect model out now.
So let's move on to the temperature binning. I explained it for most of the part, but what do we mean by temperature bins? So imagine you have 1 meter data, 365 days. For each day, we want to kind of label that day of like, are you like relatively hot, relatively, you have lower temperature in the mid temperature. But instead of doing that, for each day, we kind of summarize that day to one number. It can be mean, median, and max based on our analysis. A mean value, average temperature was a really good representative of that day. So basically, for each day, we take the mean. Imagine 365 days, we have 365 data points, bin the temperature, and each day would be assigned to each one of these bins based on the average value that it has. We could go with two routes here with the binning options that we have. One, same size bins, which means each bin has its own has the same size as the others. For example, 70 to 75 degree, 75 to 80, and so on. Or we could go to the route of having same number of samples or data points inside of each bin. So this is pretty much a little bit difference in binning, but one of them has the same size, the other one has same number of bins. These
So
two
to
options.
clarify,
Go ahead.
sorry, I didn't mean to interrupt. To clarify, Does this mean that each of the bins will have their own linear function assigned to them?
No. So basically, the goal of these temperature bins is to somehow give us a clue to the model that how hot or what is the temperature scale that we're talking about. So these are going to be extra categorical variable. So each bin, for example, you're at day, I don't know, January 1st. Okay, that day would be inside of one bin. So imagine we have 5 bins. Okay, so that categorical variable, that vector, would be one of those bins 1, the rest of it 0. So for example, 0, 0, 1, 0, 0. So it's extra categorical variable. It's not like inside of each bin we go ahead and do the linear regression or anything that we have like Caltrack. This is basically another extra features that we have.
Is it 0 or 1, or is this a 0 or 1 that is applied to a coefficient?
It's
So
a
like a slope.
vector. So let me go back here. So basically here, as you remember, we had features, then time series features, and we had categorical variable. If you remember, for month of the year, we had a vector that has 12 values, and it should be 0 or 1 each entry. So for example, for month of January, we have 1, and the rest of it would be 0. Same thing for the temperature. We have somewhere 1, the rest of it would be 0. And then we're appending all of these features together. That would be the day feature.
All right, thank you.
Okay. So this slide is basically kind of a recap of what we've done before, what's going on, how we pass these features to the model, and how we predict it. So in the bottom, you have your temperature features, features vector. In the beginning, you have temperature time series. You can, right here, you can have your solar time series. Here, we just stick to the simplest version for the non-solar meters. And you're going to have your day of the week categorical, one hot vector, and month of the year, one hot vector. And this is your model. So basically, your models is a matrix. This is a coefficient of the model. It's a matrix of 24 by the number of features you have, based on, as we know, based on our option with the features, that can be different. And each cell here shows a coefficient. Okay, the first 24 rows responsible for temperature. The next 7 responsible for day of the week. Rest of it is, and the next 12 is responsible for month of the year. And now we add the temperature bins. Let's say in this case, we have 5 temperature bins. So we have that extra added features. Those columns are related to the temperature bins, and these are 1 hot vectors. So all in all, for example, for this specific day and this specific meter, we have a feature vector of 24 plus 7 plus 12 plus 5, which is 48. Okay, so we have a matrix of 48 by 24. This is our model. This vector would be multiplied by that matrix, and then we're going to have a 24 hours prediction. And we wanted to learn any given meter, we wanted to learn what are the best values for these coefficients. Any question? I can be a little bit misleading or confusing if it's the first time you're looking at the heat map of the model coefficients. Okay. So let's move on to the results of adding temperature bins. So what was the main reason that we add the temperature bins? To solve the bias problem. What are we looking at here? Let's focus on the left figure. We have on the on the y-axis we have PNMB, which is normalized mean bias error, and in the x-axis we have the multiple temperature bins, and you can see the median of that temperature bin value. And those bar charts is the actual size of the bias. The red curve, the red bars are showing the Caltrack bias in each temperature bin. The blue one shows the new model. And when I talk about the new model in the left figure, we're talking about when we don't have the temperature bins. So basically, we predict, and based on the temperature bins, we show the error result for that. As you can see in the middle, we have high errors, but if we add the temperature bins, and the right side, the right figure, we can see the result of error for the new model with temperature bins. You can see in the middle, we have way less temperature, model bias. We still have a little bit of problem in the last bin, which based on changing the number of temperature bins, we didn't see any huge improvement on that. But the rest of the bias in general reduced significantly. And in this case, on the right side, we're using same size bin temperature for this figure. If we change the same size bins to the same number of data points in each bin, we're going to have this error profile, which basically I'm going back and forth to see the difference between that. If you can see, we have less error bias on the last temperature bin, but it's like adding bias in the middle of it, adding that extra bias in the middle of in the those temperature bins in the middle. Travis?
I just wanted to clarify that this is on the test data, the reporting year, not the baseline, correct?
Yes, for the baseline, the error profile for the new model is pretty much the same, but for Caltrack, as we know, is overfit in the baseline, way overfit in the baseline, and these are very little, so close to zero for the baseline. And we're talking about
Okay,
PNB for the bias. For the PNRMSE, root mean square, we have better results for the new model, no matter if you're adding temperature bin or not.
Right. And as far as that last bin goes, I just wanted to clarify for the audience. We have explored creating many additional bins, with the thought process being perhaps the issue that we're seeing is that the last and first bins are capturing the more normal usage. And so if we make the bins smaller, then we will capture less of the normal usage and we will find that extreme usage. However, we never found we tried 20 bins. It didn't improve the first or last bin. So right now it's somewhat of an open question on why those bins consistently seem to be larger than all of the rest.
Yeah. Okay, let's move on to the next section. So clustering daily usage pattern. This is totally new module we added to the new model. We had actually really good reason to do that, and I'll explain it in the next slide. So quick recap again. What were the features look like? We had temperature, time series, and the categorical variable. We have day of the week, month of the year, and the temperature being so far. So just in here, just for the time-based categorical variable, we had 7 multiplied by 12, so 84 categories, just for that time section of the categorical variable. If we have just 4 temperature bins, not more than that, we're going to have 336 different unique categories for a year, basically. So imagine we have 1 year, in the baseline, we have 1 year worth of data. Roughly, we have 1 day in each category, in each unique category, okay? Which is not a good thing, which means our model just relies on 1 data samples in each category to train for each, to learn a good coefficient for that specific category. In general, we can capture the patterns in general, but we're adding noises based on adding more features. So we need to somehow solve this problem. With focusing more on the time, the time categories, the time in the categorical features, we just asked this question from ourselves: do we actually have that many different patterns in each meter? Does it really make sense that we have different Mondays of January compared to the Thursday of January? And it didn't make sense that much. That's why we wanted to explore a little bit more, and we wanted to see if we can reduce the number of categories. So that's a bad animation part. I'll talk about that later. And so let's focus on this part, the time dependent aspect of that categorical variable. We wanted to, so in order to reduce that, the idea was, let's look at each category that we had. So let's say January Mondays. And for example, we have 1 year worth of data. So in that category, we probably have 4 days worth of data, okay? So we take the median of those 4 days for 24 hours. So we have a representative for that specific category. And then we will have that for all the 83 more categories that we explained. 7 multiplied by 12, 84. For each one, we take the median. So we have 84 representative. Then we cluster them. We cluster those representative. We start from 2 clusters and going up to n, which in our case was, I think in the beginning, the analysis was around 20. And we basically choose the best cluster number based on silhouette value. What is silhouette value? Is basically the variance within the clusters over the various between the clusters. So it's kind of a metric to see how good is your clustering, basically. So we wanted to see if we actually can reduce 84 to very few number of clusters, so we're going to have a better pattern recognition in our model rather than just like with the noise and having 1 sample per category. And the result was actually really promising for almost all of the IDs. So in this specific, I brought 3 different meters just as an example, but I'll explain the whole summary of what I analyzed and saw in the dataset. So in this case, for this specific meter, which looks like a commercial building, those 84 clusters, 84 categories, has been reduced to 2 clusters. As you can see, the first cluster looks, not looks like, actually, for the fact that we know that the left one, the cluster number 1, is a representative for the weekdays, and the cluster number 2 showing the weekends. And this is a commercial building, and not all of the meters, or more specifically commercial buildings, show this pattern of separating weekend and weekdays. They have their own pattern, but this specific one shows a clear cut between weekend and weekdays. And as you can see, we used to consider each one of these um, in the figure below. We have 84 categories in each column. We used to consider each one of them separately as its own category. Right now, we have two. We have blue, which is weekdays, and orange, which is weekend. Any question here?
Going back a little bit, we know that, so we're looking at the observed usage for various days, but this is going to get conflated with the GHI if it's a solar model, or sorry, if it's a solar installation site. It's going to get conflated with the temperature and all of that. Should we also represent the GHI and the other variables within this clustering?
So we are talking about features. So right now we already have raw temperature, and for the solar models, raw solar data, which is GHI in our case, and global horizontal irradiance. Our problem was the other category, the time-based, the categorical variable that kind of splitted the whole days in many categories. And in this case, we wanted to see in the observed side if we have any pattern. So far, we were focusing on the feature side, but this is just based on the observed data. So instead of thinking that we have 84 categories and each day with month combined has different pattern, we wanted to let the clustering by itself per meter decide what is the behavior, what are the different behaviors of electricity usage for that specific meter. So solar data and temperature is already being seen, so we don't need to cluster categorize them. The behavior needed to be clustered. Did I answer your question?
Not quite. So let me phrase this or restate the question and just think about a solar meter. Now, the production is going to vary day by day based on cloud opacity and time of the year and so forth. This is going to be represented in the observed by shifting usage up and down. So you're going to have an increased amount of variance in a solar meter, and that is going to cause clustering to be less effective.
Okay.
So can we somehow take this into consideration when we are doing the clustering so that we can try to eliminate as much of that variance as possible?
And so that variance would be seen inside of the clustering by itself. If like we have different dips or peaks or anything behavioral in that meter, if that's repetitive enough, then it should have its own cluster. If it's not, it should be divided it should be assigned in different clusters. So for example, let's say in the summer we expect to have higher dip for the solar panel generation, but at the same time, which I will show in the next a couple of the slides actually, but AC usage can be higher too. So these can cancel out each other. So at the same time, either you need to have the behind the meter in PV generation, so extract that to actually look at the load pattern. But when you combine them and then you have just the AMI data, it's better to separate based on AMI and then let the solar value help the production. I personally don't know how to include GHI for the cluster. If we concat it or like, I think the impact of solar would be way better seen with the raw data rather than helping to the cluster. But
My initial thoughts on this would be, so we're looking at this daily, so we would have to, just like we're doing with the temperature binning, where we're looking at it per day, we could look at something like peak GHI of that day, or average GHI of that day. And whenever you're making these clusters, if you were to do a functional principal component analysis, which would just give you a series of coefficients that could represent the usage pattern, then you could just append on that additional variable of GHI to try to match them when they look the same.
or maybe kind of do whatever we did with the temperature bins, and then use those bins and then GHI bins and probably the FPCA you mentioned, those variables, concat them all together, and then actually do the clustering on all of them. And we don't even need that temperature bins anymore. But that kind of be that's an option. But I think mixing things like that would be a little bit misleading to just like isolate that impact. Like for example, right now we can isolate the impact of clustering or isolate the impact of temperature bins. Mixing that would be an idea, would be a good idea, but I think we can explore that.
It's a thought.
Yeah.
All right, thank you.
Okay, sure. So let's go to the next slide, which is another sample of another meter. So just like go back, weekday. Here, we basically have summer versus rest of the year kind of separation. We can see we have a solar meter, and cluster number 1, based on the less number of days that we have here, it appears to be the summer time. And as you can see, we have an afternoon peak, which I think this is the AC impact for that. We were talking about California. That's why I think the AC is on for these days. And although we have higher PV generation, but AC is using most of it, that's why we have less dip compared to the other time of the year. I believe this is based on AC, and that's why when the sun is gone, still we have that peak, and that is AC. And at night we have less, probably just because of the temperature drops, and the AC temperature is set to, for example, 72, and then that's basically turned off because at night we are 72, 70, something like that. And the next cluster, as you can see, we have a couple of peaks early in the morning, and a little bit less median PV generation for these days. So this is another example, and we have 2 clusters, so we reduced 84 to 2 right now. Any question on this? If not, I'll go to the next and last example for the clustering. Okay. Not all of.
I have one.
Go ahead.
I have so that 6-1. It just seems so strange to me. So
yeah,
given that your hypothesis is that this is from summer cooling, should we try to enforce any type of continuity on these clusters in terms of time?
I don't think so, because that number of cluster can change to 3, which we'll see in the next slide. And I think we should let the data itself decide which time, so these are defined by us, day of the week and then month of the year, but data itself, based on, I don't know, maybe they cancel out each other, or somehow that plays out for that meter to like 6-1, which is June 1. I think 1 is Tuesday and June, like the median of it was like acting more like cluster numbers 1 rather than 2. What's the reason? I don't exactly know. I trust the data, but if we wanted to have if and or if and else type of statements to just concat all of these uh, categories together, then we would have a lot of edge cases, like how we can deal with commercial, residential, solar, non-solar. That would be a little bit more complex.
Yeah, that would be quite the headache to have to sift through.
Yeah.
I suppose at the end of the day, it just matters on if the population test results are superior.
Exactly. So the last example here, this is another meter ID, solar meter. As you can see, like different patterns, different median patterns can happen in different time. Like for example here, 8.3, 8.4, and 8.5, basically they're assigned to 3 different clusters. There are 3 different days, but the median shows that they're different. Maybe Monday, that a specific user is having some peak in afternoon for some reason. Maybe he has a podcast, has lots of lights around himself, or I don't know exactly, but we have like most of the days have just a simple dip, and without that big of a peak in afternoon. It's like maximum is 3 here, maximum is around 4 or 5, and here we have a little bit of bump in the morning and a little bit of bump at the end, and then solar generation in general is less for the cluster number 3. So different patterns can pop up. They're not hugely different, but they're different enough that the silhouette value chose 3 numbers, and then, for example, not 2, and then map them together. So 84 became 3 in this case. Summary of the clustering. So one thing that the main result of the clustering was with the cluster, we can actually capture the behavior of each meter rather than guessing and having kind of not having dictate the categories. Cluster actually extract these behaviors for us, reduce them from 84 to 3, 2, 3, and we can have one better model, probably faster model. We have less features, and we don't have that noise anymore. So inside of each category, instead of like 1, if you remember, now we can have 30, 40 days, so we can actually capture those main behaviors in the baseline, so we can expect and predict that as an MMV for the next year, so we can have a better and more reliable and resilient prediction. And so we can see those 84's month day categories are being reduced. Based on my analysis for manually looking at 1,000 meters, because I just wanted to look at the different cluster, it was fun. The maximum I found was 4, and the silhouette value between 3 and 4 was like it was barely different. So the last 2 clusters were so similar with a little bit of difference, but in general that was the only one that had 4. Majority of the meters they had 2, and a little bit of 3, and just 1 had 4. And we have the minimum number of clusters in the clustering, we have it's 2. If these 2 are so similar, for example, we're dealing with an industrial meter, the usage is pretty much the same all year, then this is not a big problem. Instead of having 1 cluster, we're having 2. Then those coefficients related to these 2 clusters would be so similar together, if the cluster are so similar together, which I haven't seen at all. So this is a summary of the clustering, which is the new module we added to the model, and it helped us a lot. And I pass it to you, Travis. If there's any question, let me know. Unless, uh, otherwise, we go to Travis.
Can you click for me? I'm not going to
Oh, okay.
reshare.
Yeah.
But if we can go back, I do want to mention something before we move on to the optimization. And that is that we started with a model where we did not bend temperature, where we were dictating whether or not it was Monday, Tuesday, Wednesday, Thursday, Friday, so forth, as well as the month. And the model that we have made some rather significant changes to the model, where now we are bending the temperature so that the model can basically be informed: this is a hot day, this is a moderate day, this is a cool day. That would be an example if there were 3 bends in clustering, and also reducing our judgment of deciding that it needs to be said that it is Monday, it needs to be said that it's Tuesday, and instead just allowing an algorithm to figure out what is meaningful. And all of this should result in a model that is less overfit and less biased. Now, we have, unfortunately, we're still in the process of doing the hyperparameter optimization, which I'll discuss here in a moment. But preliminary results show that both of those things that I just said, as far as being less overfit and less bias, is true. So let's go ahead and jump to the hyperparameter optimization. So previously, when we were doing the hyperparameter optimization, we only optimized on PNRMSE, which is the percentile normalized root mean squared error. Percentile normalized means that we are dividing the RMSE by the IQR of the observed. Now, in this optimization, we had 2 variables that we were optimizing, one being alpha and the other being percent %L1. We came up with some great results in terms of PNRMSE, but unfortunately, while we were digging into these results, we also found that we had temperature bias, likely because we're using a linear model to describe behavior that changes quite significantly at extreme temperatures. And so we did introduce all of these changes as far as the temperature bends and so forth, but we also decided that bias needed representation in our objective function as well. So in this version, we are optimizing on PNRMSE and PNMBE. On the right here is the definition of the RMSE and the MBE. I should note here that the absolute value should actually be on the first summation. Small little mistake there. But ultimately, this results in us getting seasonal, average seasonal bias. And this is quite the throwback to the daily model, where we had a very similar objective function. And as far as the changes that we're making in this new optimization, we have added the number of temperature bends, because we don't know whether we should have high, medium, low, as I basically described earlier, or if we should have 11 different temperature bends. We have run this successfully with the same bin size, and we are in the process of running that with the same sample count. If you can click. So the next steps are that we want to finish the hyperparameters, and we will run our population level results thereafter on the optimized coefficients. And crossing my fingers here, we're not going to find any more significant problems, and so this can be the final model. As far as what we're getting into OpenEEmeter, the data class is largely finished for the hourly model. We are beginning work on including the model class. Testing still needs to be done. Documentation, as I mentioned before, the backlog is done, and now the documentation for the hourly model can be completed. And below is a link to the documentation. And with that, thank you all for your time. If there's any questions, I will take them now, and if not, we can go ahead and close out this meeting.
I hope we don't find any significant problem.
Me too.
Yeah.
All right. Thank you, everyone, and until next time.